Welcome to today's webinar on vertical alignment optimization. My name is Erin. I'm going to be your host for today's webinar. So today we are going to focus on concepts and strategies that you can use to leverage vertical alignment optimization. So vertical alignment optimization is part of our Softree Optimal add-on, and it's a way of minimizing the costs and earthworks for a particular vertical alignment. I should say in particular, the subgrade construction costs. So today have got an action-packed agenda, so I'm going to get straight into it, but we're going to be looking at 7 different concepts and strategies pertaining to Softree Optimal's vertical optimization tool. So our first strategy, we're going to keep it very simple, and we're going to discuss vertical optimization as a starting point for your alignment design and project. From there, we're going to discuss how vertical alignment optimization is actually based on a cost model. And we'll talk a little bit about what that entails and why exact costs are really not necessary. From there, we'll go into our third concept and talk about what actually the foundation for that cost model is, which are ground types. We'll talk a little bit about how you can control your alignment shape using our vertical optimizer and the different curve positions. We'll talk about a really important but somewhat abstract concept of cross-section sampling, in particular how this might apply to longer alignments as well as ones where you've got certain different longer solve time sort of alignment shape options selected. So we'll explain that one in more detail. From there, we'll talk about how you can account for constraints as well as what kind of constraints you can include in vertical optimization. And then our final concept we're going to chat through is how you can use vertical optimization as a comparison tool, whether that's for comparing different horizontal alignments or even considering different design constraints, changing those variables between alignments and understanding what the potential impact is to cost with that. So that's our plan on a page. If you joined us in the last 2 minutes, again, we've got an action-packed webinar. We're going to do a really deep dive on vertical optimization. And as I also mentioned in my very quick intro, first slide, this is part of our Softree Optimal add-on. So if you've got regular Road-Eng, this tool is, extra. It's an add-on you can add on to the license. It has a whole bunch of pieces to it, but vertical optimization is one of the big ones. So before we really get started, if you're new to it and you're wondering, what is vertical optimization? What am I talking about? I know optimization is a buzzword. I'm hopefully going to attempt to explain it to you. So we are looking at the ground profile. And if we were to put an alignment in there, like in this case, it's a user-designed vertical, all those cuts and fills that are happening along that alignment add up to be the total earthworks of your project. Now, if you're able to use really fancy mathematics and computers, you can actually ask the tool to reduce the amount of earthworks that are being cut, that are being filled, and behind the scenes, it's also solving the problem of where does the material go? Where does it come from? Where does it go to as you look to build your road? And all those little changes that we would get through an optimized vertical, those small changes add up. They add up tremendously. We've had some research studies done on the tool, and it's anywhere between 10 to 30% of your subgrade construction costs can be reduced through utilizing vertical optimization. So what is it? Fancy math minimizes earthworks based on cost. So vertical optimization, I feel like I don't really need to talk about these because you are going to see them here in a second. What benefits really, that goes age-old benefits of anything. We're going to save time and save money, but it does give you the ability to also automatically balance your mass haul, whether that's with the inclusion of borrow and waste pits or doing so internally within the road's own materials. You can track and report your material movement. You can get the quantitative comparison, which is going to be concept 7 that we're going to chat through at the end. And you can also check the feasibility of preliminary designs. So those are some of the benefits. And in the last sort of introductory idea that I'd love to leave you with before I pass it to my colleague Matt for our first concept is really that vertical optimization is part of a larger workflow. We are obviously going to skip some steps today so we can really just hone in on vertical optimization. But before Matt got this project that you're going to see up and running, he created a terrain model. He might have used Path Explorer to figure out the best sort of landscape level position of that horizontal alignment. He started a new location project in that module. He would have assigned and configured his cross section. And then if he had Path Explorer, he would have probably used Polyline to alignment to convert that into a quick alignment with curves. And that's kind of our starting point for today. So I have gone with more time than I wanted to. So let's get into our first concept, which is that vertical optimization does not need to be complicated. You've seen us click it in a bunch of webinars in the past, and it really can be a simple starting point for your project. It can answer some key questions that you might have. Is my alignment even feasible? What am I dealing with in terms of scale of difficulty? So in this concept, we're going to keep the details simple and demonstrate how to quickly generate a vertical alignment through optimization. And with that, I'm going to do our first passing of the screen over to Matt.
All right. And yeah, so we'll do a quick vertical optimization and we'll keep it simple. So right now in my project, I've got a horizontal alignment, but my vertical alignment isn't set yet. So my alignment's just set right on ground, and my 3D view reflects that. So if we want to do an optimization, we'll go over to our Project Explorer panel. We'll click vertical options on the vertical alignment. We'll set our settings. We'll talk about those settings later on. Now, generally, we'll want to assign the minimum and maximum grade for our road. We'll want to set the minimum, I hit the wrong button. We'll want to set our minimum and maximum sag. We'll click Add Edit. I'm going to add a control point here. So when I generate my vertical alignment, if there's anywhere that I want that alignment to be at a specific point, we can hem that in. So the most common one's going to be at the start of your road. So in this case, I want to start on the road that we're coming off of. And then here, I'll hit process, I'll hit OK. We'll wait a second. Well, more than a second, but not long at all. We'll hit OK, and I can see I've got a vertical alignment now with my vertical curves. If I look at my mass haul, I am balanced, and I can see now, just kind of from that broader model perspective, well, my alignment's not just set on the ground. I've got cuts and fills being considered and modeled as a result of that. So with that, I'll hand it back to Aaron for a moment, and we'll go on to our next topic.
So our second concept that we're going to be talking about and introducing you to kind of builds on that last one, which is to help you understand where the vertical optimization is coming from. And in this case, it's based on a cost model. But the really key concept that if you're going to pick one to remember, exact costs are really not necessary. So the precise details of that costing model really don't make a huge impact. The cheapest solution is going to be the one that has the least earthworks. And in this case, it's more about having a directional relationship between your costs. So with that, Matt's going to now give you a good introduction to the cost model and the impact it has on optimization.
So with that, that optimization buzzword, we need kind of in the background, the software has to be told to either minimize or maximize something. And what we're telling the software to do is minimize our road costs, so our earthworks costs. And of course, to do that, we need to define what those costs are. So we have our ground types table, and I'll talk about this a bit more in our second well, I guess our third concept. But in this example, so far, I only have one ground type assigned, and I'm telling it that it's going to cost $3 a cubic meter to excavate, and $6 a cubic meter to place, shape, compact that material. So that's accounting for the actual digging. Now, the other thing that we're accounting for with earthworks costs is the movement of that material. So if we have to, say, cut here and haul that material back to here for fill, well, it's going to cost us some money to throw that in a truck and move it back. So we have our haul costs, and all these values are all flexible. You can put in whatever you'd like to get the costs assigned that you'd like. But again, another thing that Aaron introduced is to optimize your vertical alignment. It's relatively insensitive to these costs. So with that, we ran our optimization in that last run, and I've got a total cost of $114,000 here. We could completely change our unit rates here. So keep in mind what I'm at for free haul numbers. I've got a very expensive haul cost and relatively cheap earthworks costs. We can open up something different. So this one, my excavation costs $12 a cubic meter. Embankment cost is $4 a cubic meter, and my haul costs are, again, substantially different. So we'll hit OK. We'll see, obviously, our project costs change because we've changed that. But if we want to see, well, how does that change the actual position of our alignment? I'm going to do a second vertical alignment here. I'm going to re-optimize this with our new costs and that quite different ratio from what's haul and what's handling. We'll hit OK. And we see our mass haul changed, our total changed, but it didn't change a lot. And if we really want to, we can zoom in here and we can zoom way in. And so the magenta line is the line with the new costs. That green line is the line with the old costs, and we can see, like we said, pretty insensitive. We're pretty close, even though that we've changed those costs a lot. So with that, I'll hand it back to Aaron, and we'll move on to our next topic.
Perfect. So our next concept kind of builds on that idea of a cost model, but dives a little bit deeper into its foundation. So the costs in that cost model are based on ground types. And in the example that Matt just showed, he focused on having one ground type. Well, you can create a costing model that has different costs for different ground types. And those different ground types can be assigned to different parts of your alignment. And a really great example of why you would want to do this and include it is when we talk about something like solid rock. Solid rock is much, much, much more expensive to excavate than gravel. And you'd want the vertical alignment optimization to consider that very large difference in cost as it goes to perform its job. So in this concept, we're going to explore the idea of ground types and including their handling, excavation, and embankment costs. And for that, obviously, going to pass it back to Matt.
Perfect. And I'll share my screen. All right. So similar example, only as promised, moved a little further along in the design process. So previously, we kept it simple, one ground type. We didn't talk about really a lot of the complexity that some of you are going to be considering if you're designing by hand. And ultimately, the vertical optimizer will consider what you tell it to. So here we can see I've got, well, in my cross-section view, some different horizons for different materials. So those subsurface conditions are assigned in my assigned by range subhorizons, where I've got, in this case, gravel over fractured rock, hard pan over fractured rock, unconsolidated material, etc. So we can assign that for different ranges. And those different materials that we have assigned, so previously we were just looking at our overburden, well, we can have our gravel that's assigned as being one cost, but if we have rock, well, it's going to cost more. So we can increase that excavation rate for a rock, and the software is going to consider it. So yeah, the ground types themselves, super important. These rates are dollars per cubic meter. So with that, it's really going to consider the model as a whole. Now, aside from just the assigned by range subhorizons, other things that are going to influence your volumes include your templates. So here I've got a template with a stacked rock fill. I've got other spots along my alignment where it's kind of just your standard road, so we can change the cross-section geometry wherever we'd like. The software is going to consider it. And then other things like stripping. So in this case, I've got some overburden removal being applied. Again, software is really going to consider all that stuff that you'd be considering if you're designing by hand. So with this, still just a click of a button, we'll hit process. We can see our total costs here starting out. We re-optimize with all these extra considerations in there, and we'll see an improvement. Oh, and I forgot one talking point here, which I will hit on. So price went down, we see our earthworks changed, the actual geometry changed. Another aspect of ground types and volumes and costs, and it's assigned by range, we have pits. So here I've got a borrow or a spoil site. In this case, I've got both assigned, where if I have a deficit, I can borrow material to account for that deficit. If I have a surplus, I can dispose of that material. So again, that is assigned by range pits, or we can also access that parameter in our vertical optimization UI. And if we're looking at the mass haul, we can see those are being used by that vertical drop or vertical rise in the mass haul diagram. So with that, once again, I'll hand it back to Erin.
Awesome. Okay, concept 4. We're actually doing okay for time. I'm impressed with us, Matt. Our fourth concept really relates now to some different options that you can include to be able to control your alignment's shape, and in particular, its curve positions. So this includes an ability to include, say, a minimum tangent between curves, or to potentially, if you're doing something more of a resource road and you're looking to have it follow the ground profile a lot more, we can allow it to have back-to-back curves. So in this concept, we're going to explore those sort of different settings and concepts. And then we're going to also discuss the importance of a topic called smart curves, or say a feature called smart curves. So we introduced smart curves in version 11, and it really kind of takes the previous optimization results and improves them by removing unnecessary curves through either deletion or through merging, while still minimizing your earthworks. So the end result and the importance of smart curves really comes down to both the drivability and constructability aspects of the alignment it's producing. So concept 4, I'm going to pass it back to Matt, and we're going to talk about how you can use vertical optimization to control your alignment's shape.
Alrighty, so yeah, our alignment shape, that's kind of a difficult one to describe without just showing it. So I'm going to show where it's at in the UI here. So first, in the standards tab, the drop down that we have up here is, well, curves, fast, polylines, curves and tangents. Variable curves and tangents are user defined. So far, I've been using fast curves. And what that's going to do is, one, it's called fast because it solves fast. And two, it allows us to have stuff like this, where I've got my vertical curve, end curve butted up against the beginning of the next vertical curve. Now with this, where smart curves comes into it, is if we just let the software optimize without any cleaning up the final results, it's going to give the absolute cheapest solution, but it's not going to be a very visually attractive solution, and it's going to, well, from a staking standpoint, a lot more curves to lay out, and from a, well, just producing your drawing set, there's a lot of extra labels there. So I am going to rerun this optimization, but this time I'm going to turn off smart curves, and we'll hit process. So we can see our cost dropped a little bit without smart curves, but there is an awful lot of curves, and these curves, as introduced, they're not saving us individually, they're not saving us a lot of value, and they're certainly busy and a nuisance to deal with. So we've added that smart curve setting where we're eliminating stuff like this, where we've got a bunch of curves that are not adding or not saving much value. The actual settings in that smart curve, we have our K percentage change, which controls how the curves are merged together. And then we have our VIP reduction tolerance. So in this case, the bigger numbers you use, the fewer curves you get, but the offset is it's going to cost you a little bit more the more you clean it with smart curves. Now, so we've covered what smart curves are. I'm going to hit undo here rather than just going back. The other aspect of controlling our alignment shape that's worth talking about is, well, the solutions other than just this fast curves option. So there's a few options here. Polylines, you don't get any curves, it's just individual polylines. User defined, you could click in where you'd like your curves, and the software will move those up and down to get the best vertical alignment with the assigned curves. But here we'll talk about variable curves and tangents. So if I had a project where I didn't want to allow my vertical curves right up against my, right up against each other, we could go variable curves and tangents. We can set a minimum curve length at whatever we'd like, and we can set a minimum tangent length at whatever we'd like. We'll hit process, we'll hit OK. And we can run this with smart curves as well. So if there's short, insignificant curves that are in that initial solution, we can get rid of them. But the thing we'll find here is, well, we're not going to have any locations where our end of vertical curve is equal to the next beginning of our vertical curve. One thing we will notice though with this is it takes longer to solve. And it's going to be a more constrained solution. So those more constrained solutions are always going to cost more than a less constrained solution. But there we are. We can see here we've got the end of that vertical curve, and then 20 meters away we've got the beginning of our next vertical curve. So there are settings in there to manipulate and force that solution to be what you'd like it to be. And with that, I'll stop talking for a bit and hand it back to Erin.
Okay, awesome. So concept 5 is all about the sampling that the cross sections are being calculated at in vertical optimization. And if you've joined us for one of our webinars before where we talked about report points, this has a very sort of similar background and similar impact on your project, and in particular on your solve time. So we have an ability within vertical optimization to define how frequently we would like it to calculate the cross sections and make the adjustments to try and optimize them. So if you have a smaller number, so more frequent cross-section sampling, the accuracy is going to increase. But this, again, similar to report points in the software, it comes at the cost or the trade-off of having a longer solve time. In particular, if you have longer alignments or optimizations that are using one of those more slower solve times, like Matt just showed you with variable curves and tangents. So we're going to go in, discuss cross-section sampling, the impact it has, and a tool you can use if you aren't quite sure what type of sampling spacing you need. And with that, I'm going to go back to Matt.
So, as introduced, this concept is very closely tied to our report point sampling. And just as a brief refresher, the road design side of our software uses a cross-section model. Report points control how frequently we generate those cross-sections. Now, when we're doing our vertical optimization, we may find that there's some of those report points that land very close to each other just because they're a different class, and we might not need to sample every one of them to get a reasonable solution. So there is functionality built in the software where we can increase or reduce our sampling. So we'll pop this open, we'll go in here. So section sampled. And right now I'm sampling my alignment every 10 meters. I'm not using every one of those cross-section points. So that saves me solve time. Now, another thing that's not necessarily related to solve time, but is worth talking about as we talk about sampling, and that is our vertical control. And I'll mention accuracy as well here too. So right now I have my vertical band center set at relative to my current vertical center line. Could just as easily be ground. And we're offsetting that 10 meters either side of that. So I'm going to hit process here. I'm not going to actually run the optimization. I'm just going to do that sampling, and we'll have a look at what that looks like. So that is the vertical band that the software is considering when it's doing the optimization. So more or less, your solution can be anywhere within that green band. Now, we can see these ticks. Those are that every 10 meter sampling that we're doing. And here we're also sampling it vertically, so we can see that. Now, you may want to change that vertical band if you have a project that, well, say you were expecting some really large cuts, or so if we went through here and we knew we could go from there to there, well, that's 12%. So if I was trying to design this road with 8% and I didn't have a wide enough vertical band, it would probably fail and come back that the problem was feasible. So we can widen that out, or if we wanted to, we could also thin that out if you're on really plain, regular slopes. So we ran this previously. We can, well, reduce our section sampling. We can increase that band. We can see how that affects things here, and we'll notice that it samples quicker than when it was sampling at a 10 meter spacing. We can see the band is now wider, so I might be able to get an 8% road up there, but really we should probably move the horizontal at that point. And yeah, and if we were solving something like variable curves and tangents, since we have a reduced section sampling, this would go quicker. Now, the last thing I'll mention here before I hand it back to Aaron, if we were really being particular about what sample spacing we'd like, well, personally, I'll use between 5 and 20 meter spacing, depending on how irregular my project is. But we could kick it back to the software, come in here and click auto search, and it'll give us a recommended sample spacing to keep the confidence interval. I think less than 1% is the value that it uses. So if you're not sure and you want to err on the side of caution, that is an option. And with that, I'll hand it back to Erin.
Excellent. Okay, let's go into our sixth concept, which is going to be all about how do you add those other very project-specific details into vertical optimization. So these are your constraints and some of your design variables. So Matt introduced a couple of them earlier. He talked a little bit about min-max grades, K values, but there is an ability to add more constraints and other details, such as elevation control points, or if you're in the resource road sector, I should say, something even like full bench cut. So we can add a whole bunch of other constraints and considerations into the optimization, and doing so not just for the full length of the alignment, but we can actually start to specify these by range. And a great example is being able to specify grade constraints by range as you approach something like a wind turbine pad, or yeah, that's a really common one that we see. So with that, let's go and learn about our sixth, almost done concept about accounting for constraints. And with that, it's coming back to Matt.
All right, so I've got this example is a different project than the others. So the others, if anyone is interested too, it's the examples for that are coming right from our online training course that was just launched. So of course we're covering a lot of topics very quickly. If you'd like something more self-paced, that is an option, and the files I have been using are part of that. This one, though, I wanted something a little more visual. It's certainly included in the training package, but yeah, I just wanted something that's a little easier to see at a glance. So our vertical optimization constraints, well, general controls kind of how the software looks at the problem. Our standards, well, we control that shape, not really a constraint, but things like minimum and maximum grades certainly are constraints. So we can assign those globally, as I have here, or we can assign them for specific ranges. And this one's not really set up to be a good example for that, but as Erin said, wind farms, this is a super common parameter to use. So if you have steep roads to get to your turbine sites, you can account for that. But as your road goes through an actual pad, you can reduce those grade constraints through the pad. You can even tell it to be a linear section, so on a vertical tangent. And you can do that by station X to station Y. Control points, well, I mentioned often there's a control point at the start. You can also have control points if you have something like a bridge abutment design that you want to meet up with at a specific elevation. That's not really dictated by earthworks costs. But what I'm, I guess, most interested in talking about here is the content covered in the constraints tab. So before I actually add some constraints in, I am going to just run this without really hemming in my project too much. So that isn't a key concept from our bullet points, but it certainly is a key concept as you're working through these projects. It's always a best practice to start simple and add complexity as needed rather than just trying to add complexity for the sake of complexity. So I'm going to hit process, we'll hit OK, we'll let this thing run through, and we're going to get something that that I don't like, and I don't think anyone would. And that is this guy here, where I've got a little bit of fill falling off into oblivion. So with that, if we wanted to, we could figure out where we wanted to assign a range constraint that controls the alignment, and not just a control point where I want to be there, but we could say, well, I want it to be full bench, where anywhere from station X to station Y is entirely founded on cut. So for that, we'll go in here. I'm going to click this. I'm going to go to my full bench constraint. I'm going to click active and I'm going to assign that. So I want to assign that from station 107.7 to station 204.4. I'll click add edit. I'll click process. We'll hit OK. We'll hit OK. And while that runs, I will just mention there's other settings that we can control the vertical position of a road. So if you're overlanding a swamp, you can have a minimum embankment height as well. Or if you want to do something that's not quite full bench but control the cut depth, you can set a minimum cut depth as well. And there we are. We've dropped that down into full bench. And again, we can keep incrementally adding complexity to it if we'd like. And here we can look at it and say, well, at station, what are we at? 170, we're perched on the edge of a cliff. We're probably not moving that material ahead like our mass haul would show. So we can use some of those other settings in here to not necessarily hem in where the alignment is, but account for the way we expect this to be built and in terms of what direction our material is allowed to move. So here I'm going to add a backwards constraint. I'll say from 107.7 to 211.2. I want to only allow my material to be moved backwards, and I do have a spoil site assigned here to take that material. And we'll rerun, and we'll see a different solution. And of course, it's going to cost a bit more, but we're actually accounting for the realities of how we want to build it. So it's the optimal solution once we recognize that there's these constraints that we have to deal with. Now we're not chucking a bunch of this material ahead. The fill for this portion here is getting pulled back once we're on that benign terrain up top. So that is constraints. Last closing remark. Yeah, it's not really a constraint, but it's also accounting for all those assigned by range parameters that you'd usually assign to for different templates, etc. And with that, back to Erin.
Awesome. So final concept of the webinar kind of goes back to where we began, which is this idea that all that complexity and detail that we just chatted through isn't necessarily essential in being able to leverage the tool. So in our final concept, we're going to discuss how you can use vertical optimization as a means of comparing different alignment options or potentially even different design variables. For example, if you were to have two different case factors that you are evaluating or two different design speeds, you could compare what the impact of that is on cost. So I'm going to pass it back to Matt. We're going to go back to the sort of more simple side of optimization and look at it as a means of comparing alignments.
Cool. All right, so I've got well, a design here that's kind of an extension of the ones that we've been looking at so far. Only now I've got two horizontal alignments. I've got one that goes over here and I've got one that goes over here. Now I've got these just for the sake of a side-by-side comparison, simple or with all the gory details in them. So this one in magenta, if we'd like. Actually, I'm going to just turn off a few settings here so we can just see the stuff we want to see. So this one in magenta, if we optimize it, we can see we're at that 114,000 mark. Now this one over here, and this is a Path Explorer solution versus one that's been designed by hand. If we want to compare these two options, well, it would be really easy to do a good job with one and a bad job with the other, and we're not really doing that apples to apples comparison. But if we optimize it, we're standardizing our design effort here. So we can come in here, we can click that. And we can see we're at 63. So if we do want to compare those side by side, we're basically, I'll use rough numbers here, but we're halving our costs by going with this other option over here. If we want to look at either of those in more detail, we can of course populate a data table to look at all the gory details like cuts and fills. But yeah, just at a glance, we can see we are coming way ahead by going with this other option. So 41.52 for our total cut versus, we'll scroll down to the bottom here, 7,300 cubic meters. So totally can use it to compare entirely different options, or it could be a matter of something like this where we say, well, I want to do another option where I see what happens if we go with broader vertical curves, compare how those standards affect my costs. Well, we can do that here as well. And with the same vertical, but just comparing those different design standards while we're costing ourselves about $10,000. So with that, we've got our vertical optimization as a super valuable tool when comparing alignment options or design standards. With that, I think I've covered the stuff I was planning to cover.
Thanks, Matt. And this might be our first on-time webinar ever. So thank you all for being here for it. So we really hope you enjoyed today's content. I think it's the first time we've ever done a sort of concepts and strategies in vertical optimization. And I'm really excited to have presented it here today. So I hope you all have a great rest of your day. Thanks, everybody.
Thanks, everyone.